Okay, so we were actually working on, that is the wrong thing. I am showing you the answer and I'm going to show you the answer. Okay, here we go. So we are working on just looking at the beginning of infinite series. And so far we have done geometric series and we are doing now telescoping series. And telescoping series are series where the internal terms or the middle terms will all add to 0. And then you are able to find a formula for your nth partial sum so that you can take the limit. So we were here at this particular problem, and I said, this is where we're going to use partial fractions on this particular series. So this is, I believe, the second example in this set. Okay, and so in order to do the sum of this series, I'm going to just use partial fractions. So I am going to take 1 over n squared minus 1 and write this as 1 over n plus 1 minus 1 over n. Oh, I'm sorry. Oh, I'm doing it wrong. Let me start again. I want to write it. I'm giving you the answer. Oh my goodness, I got to stop that. 1 over n plus 1 times n minus 1. Okay, so now I can write that as a over n plus 1 plus b over n minus 1. All right, so now that we have that, we need to find our major equation. All right, so I'm going to give you guys just a few seconds to go ahead and find A and B for me, and I am going to take roll. Okay, I'm back. So what are A and B? What are A and B? This is not a, this is an easy one. An easy partial fractions. Nobody's got A and B yet? They're looking for A and B. Okay, what's the major equation? Somebody give me the major equation.
Would it be 1 equals a times n minus 1 plus b times n plus 1?
Thank you very much. Okay, so what are our roots?
-1 and 1.
Okay, good. So our roots are n equal to -1 and 1. Okay, so if n is equal to -1, we get 1 is equal to a times -2. So a is equal to -1/2. And if n is equal to +1, we get 1 is equal to b times 2. So b is equal to +1/2. Okay, so now that we have that, we're able to say that 1 over n squared plus 1 is equal to a is -1/2 over n plus 1 plus b, which is +1/2 of over n minus 1. All righty, so now what does that do for us? Well, that now says that our sum n equal, I think I started it at 2 to infinity of 1 over n squared minus 1 is just equal to the sum n equals 2 to infinity. I have a 1/2, actually I have a -1/2. So let's pull that out. So we have a -1/2. And then I end up with 1 over n plus 1 minus 1 over n minus 1. Okay, so we pulled out the negative 1/2. All right. So I'm going to pull it completely out. And so now I get negative 1/2 times the sum n equals 2 to infinity. And then inside I get 1 over n plus 1 minus 1 over n minus 1. Okay. All right. So let's look at our nth partial sums. Okay. So S1, we have negative 1/2 on the outside. And then inside, I'm going to have 1/3 minus 1. Okay, so I have 1/3 minus 1. My S2, well, I have negative 1/2. I get 1/3 minus 1. And then I have to add the second term, which again is another negative 1/2. And then I'm going to get, when n is 3, so I'm going to get 1/3. No, n is 3. So now I'm going to get 1/4 minus 1/3. So we can pull the negative 1/2 out, and that gives us 1/3 minus 1. And then we're going to get minus 1/4 plus 1/3. So we can see that these 1/3 are going to be gone. So let's look at S3. I'm going to pull the negative 1/2 out because I'm tired of writing it. So the first one was 1/3 minus 1. And the second one was, this should be a positive. The second one is 1/4 minus, I think I did that wrong. I think this is supposed to be a half. I have 1/3, I'm sorry, minus 1/2. Then the first one should be 1/3 minus 1. And the second one should be n is equal to 3. So I should get 1/4 minus 1/2. That's what I should have. Okay, now it's correct. All right, so the second one is 1/4, because n is now 3. So I get 1/4 minus 1/2. Then the third one, n is going to be 4. So I'm going to get 1/5 minus 1/3. Okay, so now I can see that the 1/3 is going to drop out. Okay, I need to go a little bit further. Let's go one more to see what we get. So S4, negative 1/2 is there. So we get 1/3 minus 1 plus 1/4 minus 1/2 plus 1/5 minus 1/3 plus 1/6 minus 1/4. Okay, so now we can get an idea of what's happening. Okay, so I can see that the numbers that are not going to disappear clearly, the 1/3 will go and the 1/4 is going to go. And in the next one, which will have 1/7 minus 1/5, the 1/5 is going to go. And the next one, so everything's going to cancel out. Okay, so we can see now we got a formula. So our formula looks like Sn is clearly, we're still going to have the -1/2. We're going to have the -1, and we're going to have the -1/2. But everything's going to cancel up until the last value, which will be, as we can see, the only thing that won't cancel will be the 1/n+1, because the 1/n-1 is going to be gone. So the only thing that will be left is 1/n+1. Okay. All righty. So now the sum then, n equals 2 to infinity of 1/n² - 1 is going to be the limit as n approaches infinity of the nth partial sum. That is going to be the limit as n approaches infinity of -1/2 times -3/2 plus 1/n+1. And clearly, as n goes to infinity, this term goes to 0. So the sum is just 3/4. Okay, any questions? So the hardest thing is this step. I think this is the hardest step of all. And that is here, trying to find the formula. For the nth partial sum. Okay. All right, any questions about that? All righty. Well, that's the end of module 6. Module 7 starts with the divergence and the integral test. So I'm going to continue this video with this. So in this section, we're going to use the divergence test to determine whether a series converges or diverges. We're going to use the integral test to determine the convergence of a series and estimate the value of a series by finding bounds on the remainder terms. So I'm not sure if we're going to get to all of that in this section. We're definitely going to do goals, objectives 1 and 2. Okay, so let's just do a simple review here. Okay, so what we've done so far is we've looked at the geometric series test. And the geometric series test, we said that this geometric series had to be in a specific form. That was a times r to the n-1, and it actually sums to a over 1 minus r if the absolute value of r is less than 1. Otherwise, if the absolute value of r is greater than 1, the series diverges. Okay, greater than or equal to 1. Then we looked at the telescoping series, and for the telescoping series, we can find the nth partial sum. And then we look to see if that nth partial sum gives us a number. If it does, the series converges. Otherwise, the series diverges. So we just completed those two. I told you there are 12. Okay, so we are looking at the next one. So the next test is the nth term test of divergence. So this is test number 3. Nth term test of divergence. Okay. So it is a known fact that the only way the series summation AN converges, so if this series converges, I left out the word converges, then AN must go to 0. There's no way the series can converge if AN is not going to 0. Here is the test. The test says that if the nth term does not go to 0, then the series diverges. This thing in blue is what I want you to remember. This is the test. Okay, let me highlight it for you. If it'll let me. I don't think it's going to let me. It's not going to let me. I don't know why I'm having trouble, but it won't let me put a square around it. It just won't. Okay, so that's fine. So if the nth term does not go to 0, then the series diverges. So this is the nth term test of divergence. So the first thing you do is look to see, is this a geometric series? If it's a geometric series, apply the geometric series test. Look to see if it's a telescoping series. If it's not a telescoping series, then we're going to look at the nth term test of divergence. It says, if AN does not go to 0, then the series diverges. It does not say that if AN goes to 0, then something happens. We don't know. Okay, so so here I have some examples. So actually, before I go through this example, I want to make this very clear. Okay. If summation of n equals, oh no, if, that's I don't want that. I don't want all that. I just want something simple. If AN goes to 0, we know nothing. Test is inconclusive. So if AN goes to 0, I cannot make a conclusion. All right, if AN goes to 0, we got to try another test. Okay, so let's look at these examples. So the first example is the summation n equals 1 to infinity of 2n minus 1 over n plus 1. Okay, so what is AN? So AN is 2n minus 1 divided by n plus 1. So what is the limit as n approaches infinity of AN? It is the limit as n approaches infinity of 2n minus 1 divided by n plus 1. How do you compute that limit? How do you compute that limit? There's several ways to compute this limit. You can divide by the highest power of n, or you can use L'Hopital's rule. Because on first pass, you get infinity over infinity. So now if I use L'Hopital's rule, then this thing becomes the limit as n approaches infinity. The derivative of the top is 2 and the derivative of the bottom is 1. So this is equal to 2. 2 is clearly not equal to 0. So this series diverges. Okay. All right, any questions about that? I looked at exactly what it told me to do. I looked at the summation, n equals a limit there. I looked at the limit of an. If an does not go to 0, the series diverges. An went to 2, series diverges. Okay, any questions? Number 2. All right, so here's a series. Actually, I do not need the parentheses. I don't know if it'll let me get rid of them. No, it will not. So the parentheses are going to stay there. It's fine. Okay, so here's the series. An is the fourth root that is supposed to be the nth root. Is the nth root of 4 to the n times n. Okay. We can also write that as 4 to the n times n raised to the 1 over n power. So we can then write that as 4 to the n times 1 over n just gives you 4 times n to the 1 over n. Okay, so we simplified it. So the limit as n approaches infinity of an is the limit as n approaches infinity. We simplified this to 4 times the nth root of n. Now, if you remember, this was one of those special limits. Okay, the nth root of n goes to 1. So this goes to 4 times 1, which is 4. That is not equal to 0. Okay, so this series diverges. It's just that simple. Okay, but you just have to know how to take the limit of your function. Okay, a nice easy one. All right, nice easy one. Number 3. All right. An is 1 over n cubed. What is the limit as n approaches infinity of 1 over n cubed? Somebody tell me what that is. Okay, I see something in the chat. It is 0. That is correct. Thank you, Celine. So this limit is 0. Okay. Oh, wow. I got 0. So what does that tell me? It tells me absolutely nothing. So all I know is that the nth term test of divergence is inconclusive. That's the best I can do. If it goes to 0, we know nothing. Okay, you got to remember that. A lot of people think if it goes to 0, it converges. It does not. If it goes to 0, we know nothing. All right, any questions about the nth term test of divergence?
I have a question.
Yes, Dominique.
So if it goes to 0, do we use like another test to
You
find
have
it?
to use another test.
Okay.
So of all the, we have, again, like I said, we're going to have a total of 12 tests. So
Okay.
there are going to be many more tests that if you use this nth term test and it doesn't work, it gives you 0, then I say, oh, well, that's the default factor. I can't use that.
Okay.
All right. So here's a summary. All right, so the summary of the nth term test of divergence. If the limit is equal to L and that number is not 0, it diverges. If the limit is equal to 0, the test is inconclusive. Use another test. That's important. Okay, any questions about the nth term test of divergence?
I think the second example confused me a little bit. I wasn't too sure.
Victor, are you asking a question?
Yeah, sorry, I'm sorry if it's the sound.
Okay, now I can hear you.
Okay, sorry. It was for question 2 for the term test. I wasn't
Number
too sure.
2,
That's right. I think it was. I think when taking the limit, you just when you plug after taking the limit, we plug in 1 for n and then go from there. Or I think it was
are
just
you talking about here in number 2, where at the limit value?
yeah.
Okay, so this limit as n goes to infinity of n to the 1 over n was one of our special limits that I gave the other day when we were talking about sequences. So this limit is 1.
Okay.
Okay,
Thank you.
you're welcome. All righty. Next is the integral test. Okay, so here's the integral test. I'll give you some time to write it down. It says we have a sequence, an, and all the terms are positive. So we're not don't have any negative terms. We're not alternating or anything like that. We're going to write f of n as a sub n. So whatever a sub n is, we're going to write it as a function f. Okay, so we're going to take a sub n and write it as a function f. So if we have the sum n equals 1 to infinity of e to the negative n, then our function f of x will be e to the negative x. So that's what I mean. So whatever function that we have, or whatever value we have for an, we're going to transform it into a function. Okay, so when we do that, all right, this function is a continuous positive and decreasing function. All right, then we can say that either that the sum from some point capital N to infinity and the integral from that same point n to infinity of the function that is defined by a sub n, they either both converge or both diverge. So that's the integral test. So the integral test says they either both converge or they both diverge. Okay. All right, so here is the first example. It is the harmonic series. You need to know this, that the harmonic series is defined by this value. This is the harmonic series. Okay, it is the sum. I don't like that. I want that black. From n equals 1 to infinity of 1 over n. It is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, and it keeps going. This series, we have to determine whether it converges or diverges. So I am going to use the integral test. Okay, so we're going to use the integral test. Okay, so here a sub n is 1 over n. So I'm going to let my function f of x be 1 over x. Okay. So now we have the sum n equals 1 to infinity of 1 over n, and its counterpart is the integral from 1 to infinity of 1 over x dx. There's a relationship that we are going to use between these two. Okay. So what I want to do is the integral test says both of these converge or both of these diverge. That's what the integral test says. So if this integral 1 to infinity of 1 over x dx converges, then the series will converge. If this integral diverges, then the series will diverge. All right, so now let's compute. And I think we've actually done this already. The integral from 1 to infinity of 1 over x dx. I'm pretty sure we did. So that is the limit as t approaches infinity of the integral from 1 to t. Okay, remember, this is an improper integral. It's going to infinity. 1 over x dx. Okay, so this is the limit as t approaches infinity. What is the integral of 1 over x? Oh, people.
Natural.
What did you say?
Saying natural log.
Natural log, thank you. Natural log of the absolute value of x, evaluated from 1 to t. So this is the limit as t approaches infinity of the natural log of t minus the natural log of 1. And as t goes to infinity, the natural log goes to infinity. It doesn't matter that we're subtracting off 0, this goes to infinity. Okay, so we are conclusion. Integral diverges. Hence, sum that the series diverges as well. Okay. Any questions? So now you need to remember the harmonic series always diverges. 1 over n will diverge. Okay. Any questions? The next one's a little bit more challenging. Okay. Whoops. Second example for this section. Okay, so this is a series. Summation n equals 1 to infinity of n times e to the negative n squared. All right, we haven't written out a series in a while, but this one is obviously, I'll write it out. It's e to the negative 1 plus 2e to the negative 4 plus 3e to the negative 9 plus 4e to the negative 16 plus ... plus n e to the negative n squared plus ... Now the question is, can I sum up the entire series. Okay, can I sum up the entire series? All right, so let's see. What's my function going to be? What is f of x going to be? Somebody give me f of x. Let me know you guys are paying attention. What's f of x? Ooh, anybody paying attention?
It's actually to
I can't hear you, Victor.
I'm sorry. Is it n times e to the negative n squared, or is it supposed to be?
Okay, so it's x times e to the negative x squared. Okay. All right. So therefore, I have two pairs. All right, so I have the sum n equals 1 to infinity of n e to the negative n squared. And then I have the integral from 1 to infinity of x e to the negative x squared dx. And those two are pairs. So if the integral converges, the series converges. If the integral diverges, the series diverges. All right, so now we need to compute the integral from 1 to infinity of x e to the negative x squared dx. That is the limit as t approaches infinity of the integral from 1 to infinity of x e to the negative x squared dx. How do I compute this integral? What do I do? And that should be a t at the top. What do I do?
Isn't it by parts?
Okay, actually, this one is not by parts. It looks like it. If this was just negative, oh, yeah, if that was just negative x, I would have to do it by parts. But because it's negative x squared and its derivative is sitting near it, I'm just going to use u substitution. Okay, but thank you. That was a very good guess, Peyton. There was really only two ways to look at this, which was by parts or use substitution. I thank you for answering. Okay, so we'll let u equal negative x squared and du equal to negative 2x dx. And then x dx is going to be negative 1/2 du. And then when x is equal to 1, u is going to be -1. And when x is equal to t, u is going to be negative t squared. All righty, good to go. So this is now the limit as t approaches infinity of the integral from -1 to negative t squared of e to the u and x dx. Well, I already know, here it is, x dx is negative 1/2 du. Okay. So now I get the limit as t approaches infinity. Oh, I wanted to pull that negative 1/2 out. Let it not bother me. The limit as t approaches infinity. What's the integral of e to the u? I should have 15 people screaming the answer. All fighting for recognition.
You said the integral of e to the u.
Yes.
Wouldn't it be e to the wait? I forgot. I think it's like e to the u.
Okay,
Um,
that's it.
that's it, right?
That's
Okay.
it. Yep. Thank you, Malcolm. E to the u evaluated -1 to negative t squared. So this is -1/2, the limit as t approaches infinity. Okay, so so when I put in the first one, I'm going to get 1 over e to the t squared. And then when I put in -1, I'm going to get 1 over e. Now, as t gets huge, very, 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 very large, e to that gets even bigger, and 1 over that goes to 0. So this term goes to 0. So my answer is 1 over 2e. I like 1 over 2e. It's finite. Okay, so we conclude the integral converges, hence the series converges. All right, any questions about that? All right, so once we paired this series with this integral, they either both want to converge or they are both going to diverge. All right, any questions about that? Okay, so notice in the last two tests that we did, which is the nth term test of divergence and the integral test, we actually don't know the value of the series. Okay, so for the integral test, the value of the series or the actual sum of the series is unknown, but we know it converges to something. Okay. And for the nth term test of divergence, if the series converges, we know it converges. We just don't know what the sum is. All right, so we know the sum when it converges for a geometric series and a telescoping series, but we do not know the sum for the integral test and the nth term test of divergence, even though they converge. We don't know what the sum is. Okay, test number 5. We just smoking along, guys. All right. So test number 5 is the P-series test. All right, it has a certain form. You will know something is a P-series because it will look like sum n equals 1 to infinity of 1 over n to the p. Okay, 1 over n to the p. All right, so some examples. The first one, what is p in the first one?
2.
2. Okay, what is p in the second one?
Is it 1/2?
1/2. And what is p in the third one?
0.001.
1.001. Okay, so this is the P-series test. All right. Okay, we are going to use the integral test. to help us determine when the P series actually converges or diverges. Now, what happens when P is 1? Does anybody know? What happens with P? Uh-oh, this is missing an X to the P. Okay. What happens when P is 1?
Would you not be able to use the P-series test?
Well, we could, but if P is equal to 1, we get a special series. What series do we get when P is equal to 1? We get sum of 1 over n. What series is that?
Oh, harmonic series.
Yes, we get the harmonic series, which diverges. Okay, so we don't know anything else yet, but we know that the series is going to diverge if P is equal to 1, okay? Because the harmonic series diverges. So we already know this information. Okay, so now we need to see what happens for P less than 1 and P greater than 1. Let's use a nice cool color. Ah, that's fun. Okay. So what we are going to do is we are going to use the integral test. And if you remember by the integral test, if one converges, then the other converges. Okay, so if the integral from 1 to infinity of 1 over x to the p converges, then the other one will converge. Okay, so let's compute now. The integral from 1 to infinity of 1 over x to the p dx. All right, so I'm going to rewrite that as the limit as t approaches infinity of the integral from 1 to t, and I'm going to move my x to the p to the numerator, and I'm going to make it x to the negative p dx, because it's easier to integrate that way. Okay, so I get the limit as t approaches infinity of what happens when I integrate x to the p. Well, how do you integrate that? You add 1 and divide by it. Okay, so I'm going to get x. I'm going to add 1, so I'm going to get negative p plus 1. Then I'm going to divide by negative p plus 1, which is 1 minus p. So let's just, and then I'm going to evaluate this from 1 to t. Okay, I'm going to rewrite it. The limit as t approaches infinity of, so actually, let me write it. This is 1 minus p. Well, I'll just write it here. So I get t to the 1 minus p divided by, sorry guys. Sometimes I think too fast. And when I do, I just have to backpedal. Okay, good. The sum, t goes, no, just, nope, I need a limit. I need a limit first. There's so much in this one little problem. I got limits and, okay. Now, when I put t in, I'm going to get t to the 1 minus p. And then when I put 1 in, I get minus 1. Okay. T is going to infinity. T is going to infinity. So if P is greater than 1, you get the limit as T goes to infinity of T to the 1 minus P. That's T to a negative number, which gets smaller. That goes to 0. And if P is less than 1, you get the limit as T approaches infinity of T to the 1 minus P. And that goes to infinity. Okay. Okay, so there we have it. The only way this thing converges, this will equal 1 over P minus 1. If, and this is only if, P is strictly greater than 1. Okay, so if P is strictly greater than 1. All right, so now we know for the P test, the integral converges only if P is greater than 1. So that says the same thing. Hence, series converges only if P is greater than 1. Okay, so that is the P series. So the P series is the easy one. This is an easy test. Oh, so easy. It's a oh so easy test. All right, Peyton gave me the value of P earlier. So what happens to A? In A, P is 2. Series converges. Oh, you can't see it. In B, P is a half. Should have said that's less than 1. So the series diverges. C, P is 1.001. We don't care how small that is, it's still bigger than 1. So the series converges. Any questions? It's just that simple for the P test. P-series is just that simple. Okay, so we're getting ready to do, these are in the next section, direct comparison and limit comparison test. We may get to that, but I do want to go over some questions. Okay, so the first thing we did was the geometric series test. And then we did the telescoping test. Okay, so they are in red. All right, so these series we can sum. All right, so we can sum series and the telescoping series. So on the test, it will say, identify the type of series, determine if the series converges or diverges. If it is a series where you can find the sum, you must compute the sum. So for geometric series, we can find their sum, and telescoping series. So I put them in red to be special all by themselves. Okay, so geometric series, we can find the sum of the geometric series and the telescoping series. Any questions about that? Okay. There's only one test that does not tell us whether a series converges. So the nth term test does not tell us if a series converges. All right, so that's why it's in black. Nth term test of divergence does not tell us if a series converges. Okay. Trying to give y'all little notes along the way. It does not tell us if a series converges. It only tells us if a series diverges. Okay. These next four tests and the rest of the tests that we're going to do all will tell us whether a series converges or diverges. Okay, any questions on any one of these 5 tests? Let's see where we are in our syllabus.
Well, it's not really a question. I just get confused when you're doing the telescoping series, like when you do like S1, S2, S3, like how you get each number, if that makes sense.
Okay. All right, so I'll give you another one. Let me find a good one, because I don't like making them up. When I make up stuff, it's too hard. I gotta find something somebody else already made up. Okay, infinite series. Where is the telescoping series? That's the angle test. Huh. Oh, here's one. Take the sum. N equals 1 to infinity. Of 1 over n times n plus 1. Okay, that's a telescoping series. Okay, so what is an? That's what I'm asking you, Peyton. What is AN?
And is 1 over n times n plus 1.
Good. Okay, so AN is 1 over N. Okay, so that is not written in the right form. So I need to take it and write it so that I can actually see it's telescoping. So I'm gonna do partial fractions. So I have 1 over N times N plus 1. I'm going to write it as A over N plus B over N plus 1. Major equation 1 is A times N plus 1 plus B times N. My roots are what, Peyton? N equal to
-1,
and
0.
0. Okay. So we're going to use N equal to -1. I get 1 is equal to B times -1. So B is -1. And then I do N equals 0. And I get 1 is equal to A times 1. So A is 1. Okay. All right. So now my AN is written as 1 over N minus 1 over N plus 1. Okay, do you see that? So that's my AN. So now my sum, N equals 1 to infinity of AN is equal to the sum, N equals 1 to infinity of 1 over N minus 1 over N plus 1. Again, that thing in the brackets, this is my AN. This whole thing is AN. So my nth partial sum is to sum up the terms. So S1 is just A1. A1 says put 1 in for N. So I get 1 minus a half. Because I put 1 in for N. S2 is A1 plus A2. So A1 is 1 minus a half. But A2 says put 2 in now. So I get 1/2 minus a third. So S3 is A1 plus A2 plus A3. A1 is 1 minus a half. A2 is 1/2 minus 1/3. A3 is 1/3 minus 1/4. Okay, so now I got a pattern. Okay, I can see stuff drops out. I can see 1/2 goes here. I can see 1/2 and 1/3 go. So now it looks to me as if I were to do the SMth term, which would be A1 plus all of them, all the way up to AN. Everything's going to cancel out except for 1 and this last term over here, which will be 1 over N plus 1. It's the only one that's not going to get canceled out. Everything in between is going to be canceled out. Even the 1 over N will be canceled out with the 1 before it. So I get that. So therefore the sum, N equals 1 to infinity of 1 over n times n minus 1 is the limit as n approaches infinity of the nth partial sum. But that's the limit as n approaches infinity of 1 minus 1 over n plus 1. And that goes to 0. So I just get 1. And I'm done. Peyton.
Yeah, I see it better now. I was just confused, like, I don't know, like
Yeah, I
adding
think-
one.
Yeah, the hardest part is understanding that n plus 1 over n minus 1 over n plus 1 is the whole an. So you have to do one for each.
Yeah. Okay. Thank you.
Any questions?
I have a question.
Yes.
If you scroll up to where it says 8n equals, why is it, why'd you do a negative instead of just a positive? 1n minus instead of plus? I'm just wondering.
What do you mean?
So for, it says an equals 1 over n minus, why is it a
Oh,
minus?
because b was -1.
Okay, I just want to make sure.
Yep, a was 1 and b was -1.
Okay, thank you.
Good question. Anybody else?